This screencast corresponds to Chapter 4 about forces, vector diagrams, and friction. Let's imagine that we have a horizontal surface. Let's get the pen working here. There we go. That we have a horizontal surface, and there's an object on it resting on that surface. We know, of course, there's going to be a force of weight that we typically draw acting straight down. You can have F sub W. You could call it the force due to gravity. You could just use the letter W like your book does for the force of weight. And we know that there must be an equal and opposite force acting upward, which we call the normal force, which your book just calls N. And if these two forces are the only forces acting in the y direction, then of course they must be equal and opposite. So I'm going to adjust this a little bit. There we go. So my up force should equal the down force. And of course the object is not moving laterally or horizontally at all. Now let's suppose we decide we're going to pull it with a force, we'll call it an applied force, acting to the right. If this is all we have, and if the force of friction equals 0, or we could say the coefficient of friction equals 0, then we do not have an opposing force, which would be going this way if it existed. And so we have a net unbalanced force. So if we take the summation of our forces in the y direction equaling 0, what that means is that the normal force must equal the force of weight. And the summation of forces in the x direction do not equal 0. And if they don't equal 0, then they have to equal ma. And it turns out that the unbalanced force in the x direction is F sub A. So we have these two equations right here, this one, and we have this one. And so depending upon what they give us in the problem, we should be able to solve those other things, for those other variables. Now let's suppose that there is a force of friction, and so that means this is no longer true, and this is no longer true. That means we do have a force of friction acting in the opposite direction. Now, let's say that this object is not accelerating. If it's not accelerating, that means that the summation of the forces in the x direction equals 0. In other words, we would say that acceleration equals 0. The summation of the forces in the x direction must equal 0. And those forces would mean that my force of friction, F sub F, must equal the applied force, F sub A, if we're moving with an acceleration that's equal to 0, which is another way of saying at a constant velocity. Hopefully that makes sense. And so now our equations are going to be this one right here, up equals down, and our equation is going to be here, left equals right. And as soon as we have a force of friction, it also means that there's going to be a coefficient of friction, which is going to be the force of friction divided by the normal force. And we can say, therefore, that the force of friction is going to equal mu times the normal force. And since from up here, the normal force is the same as the force of weight, the force of friction is going to equal mu times the force of weight when we substitute F sub W in for the normal force F sub N. And so now I have this equation right here, and I have this equation, which I can use in order to solve the problem. Typically, you're going to have the information you need for the force of weight, which would be the mass times the acceleration due to gravity. And let's fix that. The force of friction in this case is going to equal to mu times m, the mass, times g, the acceleration due to gravity. And of course, if the force of friction equals this, and the force of friction equals this, then we can say that F sub A, the applied force, equals mu m g. All right, let's move along and let's try something different. In this case, let's have our horizontal surface with our box on it. There's my force of weight. We're going to have a normal force equal and opposite. Not necessarily equal, as we'll see later. It all depends. And this is my normal force. And let's say we have an applied force. And we have our force of friction. But let's say it's going to be accelerating to the right. So my acceleration is going to be greater than 0, which means we do not have constant velocity because we're accelerating. And then we're going to say we're accelerating to the right due to the applied force. Well, again, in this particular case, we would make certain observations that my up force, Fn, must equal my down force, F sub W, which is another way of saying that the summation of the forces, and that is an ugly summation sign, bothers me more than it bothers you. And so I'm going to try a little better with that. The summation of my forces in the y direction must equal 0. Remember, one of these forces is negative, which is why when we add them up, they equal 0, because the other force is in the opposite direction. One has to be negative. Now, as far as the summation of the forces in the x direction is concerned, my bigger force, F sub A, minus my smaller force, F sub A, F is what's causing the acceleration. And anytime you do not have constant velocity, but there is acceleration, the unbalanced forces must always equal ma, mass times acceleration. Remember Newton's second law, F equals ma. Unbalanced forces equal mass times acceleration. It takes an unbalanced force to accelerate an object. Otherwise, it's going to keep moving or stay stationary in whatever state it's in without that unbalanced force. Now, once again, of course, we can think about simplifying certain things. Because we have a force of friction, once again, my mu is going to be the force of friction over the normal force. And so my force of friction is again going to be mu times the normal force. And my normal force is again the same thing as F sub W, as it says over here. And so that's mu times F sub W. And of course, W is mass times gravity. Mu equals mass times gravity. Force of weight is mass times gravity. So now I have this equation right here, which derived from this equation and the forces moving horizontally. And I also have this equation up here. So now I can say that my applied force minus my force of friction, which according to the box here is mu mg, is going to equal mass times acceleration. And most likely in a math problem, you would be given mu, you'd be given m, you'd know that g is 9.8, and of course you still know m. And so you could find the applied force, or you could find the acceleration. Or if they gave you those two things, you could find m. Or if they gave you the applied force and the mass and the acceleration, you could find mu. All kinds of possibilities there. All right, let's go to something different then. What if we have a horizontal surface and we have a block on here and we have my force of weight, we have my normal force. Notice I'm drawing all my vectors acting from the supposed center of mass of my object. And let's suppose we have an applied force acting at an angle. And that angle is some angle theta. And because this is going to be going to the right, that means we have a force of friction acting parallel to the surface in the opposite direction. Now, whenever we have a vector that is not acting along the x or the y axis, remember we resolve it. So if I resolve my applied force into my horizontal force and into my vertical component right there, and to make a parallelogram, and then I'm going to label these. This force right here is going to be my applied force times my cosine of theta. And this force right there is going to be my applied force times my sine of theta. Moving pretty rapidly here, so pause the screencast if you need to think about that for a minute. So now let's suppose that my acceleration is 0, which means I have a constant velocity. This phrase, constant velocity, is often something that is overlooked when students attempt to do problems like this. Another point, please notice that I have two vectors acting upward. I've got this vector acting upward, which is the normal force, and I have that vector acting upward, which is the vertical component of my applied force. So now, when I do my summation of my forces, the summation of my forces in the x direction must equal 0 if there's no acceleration, which basically means that my force of friction must equal my Fa cosine theta, which is the only other force acting in the x direction. Also keep in mind something that will be helpful, like we've done several times already. If mu equals the force of friction divided by the normal force, then my force of friction equals mu times the normal force. And I can plug this in for F sub F. So I have mu normal force equals Fa cosine theta. Now let's look at the summation of my forces in the y direction. I forgot the F up there. And in the y direction, they equal 0 because it's not accelerating up or down. It's at equilibrium. And so that means my up forces must equal the down forces. Just like up here, my left forces must equal the right forces. Or in other words, the summation of the forces equals 0 in each of our two dimensions. So my up forces, there are two of them. We have my F sub n, and we also have the Fa sine theta, the vertical component of my applied force. The down force is F sub w. And F sub w equals mg. And now you see we have this equation right here, And we have this equation right here. They both have the normal force in there. Or if we wanted to, we could solve for everything in terms of the force of friction, where the force of friction is mu times, normal force, would be F sub F over mu. And typically, you'd be given mu, and you'd be given your angle, theta. And you know what G is going to be as long as you're on the surface of this planet. And typically you're given mass. And so you have enough information to solve for those other forces. Now, let's change things around a little bit. And let's say that we're going to be accelerating to the right. So if we're going to be accelerating to the right, that means that, and let's change colors here. Let's go with green. If we're accelerating to the right, acceleration is greater than 0. That means my velocity is not constant. My velocity is going to be increasing as well. And therefore, we would say that the summation of my forces in the x direction no longer equals 0, but instead it equals ma. And so I would take my bigger force going to the right, this one, Fa cosine theta, and subtract the smaller force, mu F sub n, and that is going to equal the unbalanced force called ma. And again, you have that equation. Sometimes you're going to need that equation. And we also have this equation, right there. And we've already gotten rid of F sub W. So we've got 3 equations there if we need them. Now, let's look at the situation where we have an object on an inclined plane. There's my block. There's my force of weight. My normal force is perpendicular to the surface. Don't draw it vertically. It's perpendicular to the surface. And let's ask this question. If the object is sliding down the plane with a constant velocity, so we're going down the plane and my acceleration is equal to 0, which means constant velocity. What can we say about this? Well, once again, we always resolve vectors not acting along the xy. And so we're just going to shift the axes a little bit. There's my y-axis. There's my x-axis. And so I'm going to resolve my weight vector. Every time you have an object on an inclined plane, resolve the weight vector into its 2 components, making your parallelogram. And when we do that, this vector is going to be my force of weight times my cosine of theta. And by the way, I should point out that this angle here is the same as this angle there. That's very important to know that. You could create similar triangles if you wanted to and prove that to yourself, that those 2 angles, the angle for the actual triangle representing the solid incline resting on the surface of the earth, and the angle representing the components of the weight vector, that's the same, always will be the same angle. And then this vector right here is going to be my weight vector times the sine of theta. So as we begin to draw some conclusions, if we are going, if there is no friction, let's say that the force of friction equals 0, and let's say that mu equals 0, then there is no force acting up the plane. The only force that is working horizontally along the x-axis is going down the plane, which means that's going to be actually going to be an unbalanced plane. So I'm going to hold off on this for a minute. I'm going to come back to that. And basically we're going to say then that my normal force acting perpendicular or normal to the surface is going to equal the y component of the weight vector, cosine of theta, because it's not accelerating in the y direction this way. And we can say that the unbalanced force acting down the plane, which is Fw sine theta, equals ma. Unbalanced forces always equal ma. And there are my equations. There is no mu. And if, however, there is friction, so I'm going to cross that out, that means we're going to have a force of friction acting up the plane. And let's ask this question. What does it take for the box to move down the plane with constant speed? At what angle theta will the box move down the plane with constant speed and there's no applied force? No applied force. So let's analyze this situation. So the first thing that we're going to say is, in the y direction, the summation of the forces equals 0. So F sub n equals F sub w cosine theta. We also know that because we have friction now, that mu equals the force of friction over the normal force. And so therefore the force of friction equals mu times the normal force. The next thing we're going to do, this is going to be in the y direction. In the x direction, we have no acceleration, so this means that the force pulling it down, which is Fw sine theta, must equal the force holding it back, which is the force of friction, and the force of friction equals mu times the normal force. Now, as we begin to solve this equation for mu, we can see that mu, right there, is going to equal Fw sine theta over F sub n. But F sub n equals this. So I still have Fw sine theta in the numerator, and in the denominator, instead of mu times F sub n, I'm going to substitute this in right up here, Fw cosine theta, and look at that. The weight cancels out. In other words, the mass is irrelevant. It doesn't make a difference in this problem. And you might remember that sine theta divided by cosine theta equals tangent theta. So that's a very, very helpful identity. Mu equals tangent theta when we are at the angle at which the box is going to slide down the plane at constant speed. Now again, we are talking about the coefficient of kinetic friction, not the coefficient of static friction. So you might have to give the box a little push to overcome the greater static friction, and then it'll move down the plane at constant speed. And so sometimes you're given mu, and you can solve for the angle, and sometimes you're given the angle, and you can solve for mu. And this saves you a whole lot of work. If you get a multiple choice question on, let's say, an AP physics test, and I'm just speculating here, that rather than do all of this work and all of this diagram, you just jump right on this identity for moving at a constant speed down a plane of angle theta when there is friction. Now, let's look at this situation. What if we have our inclined plane and there's our object sitting on the plane, and we want to move up the plane with a constant speed? So there's my applied force. We're going to be moving up the plane with a constant speed. So that means acceleration equals 0. And in this problem, let's just go right away to the fact that there is going to be a force of friction that's going to be acting down the plane. And we resolve my weight vector into its two components. So here's my y component. And by the way, this component right here in the y direction, this is my FW cosine theta, because this is theta and this is theta. This is what is equal and opposite to the normal force. And that's this vector right there. And then this component right here is my FW sine theta. Now, please keep in mind that this force is not the same as my force of friction. These are two different independent forces acting down the plane because the object is going up the plane. Friction always opposes motion. So when we talk about what's going on in the x direction, the up force equals the down force. My applied force up the plane equals two forces acting down the plane, which is the force of friction, and it's also my component of the weight, Fw sine theta. Once again, we can remember that mu, because we have friction, there's a mu, F sub F over F sub n, and therefore we can say that F sub n equals F sub F. F sub F equals mu times F sub n. And we can substitute that in right here. So we get my applied force acting up the plane is mu F sub n plus F sub w sine theta. And of course, F sub w is mg. And I could substitute mg in for Fw. And again, I have enough equations that I've put together. Up equals down, and which was right up here. And by up, I mean out of or normal to the surface. And down, I mean going down perpendicular to the surface. And then I also have up the plane, which is Fa, equals down the plane, which is this. And I've got my several equations again. Now, the last thing we can do is make this problem even more interesting. And if I draw my inclined plane, put my block here, and let's say that we are applying a force at an angle on the plane. So we have Fw acting down, and we have force of friction acting down the plane. Now we're going to resolve our two vectors that are not acting on the x and y axis. What happened there? Okay. Here we go. There's my F sub W acting down. Make sure when you make this triangle, by the way, that the opposite component, this one right here, is parallel to the surface of the plane. Sometimes I see students do this, and you do not want to be that kind of student, where then when they go to make this triangle, they make it like this. Don't do that. And so I'm going to erase it out of your memory, out of your consideration. And this is going to be theta. This is going to be theta. This is going to be my hypotenuse FW times sine of theta. And this one right here is going to be my hypotenuse times my cosine of theta. However, we've got that other vector that's acting at some different angle. Makes a parallelogram. Let's call this angle phi, I think that is. And this is going to be my applied force. And so this component right here is going to be my hypotenuse, F sub A, times my cosine of phi. And this component right there is going to be my hypotenuse, F sub A, times my sine of phi. And then, of course, let's not forget my normal force. Hopefully we got enough vectors here for you. And so now we have to find out in the problem, are we accelerating up the plane or not? And just for the sake of argument, let's not be accelerating up the plane. So my acceleration is going to equal 0, which therefore means, regardless of the acceleration being 0 or not, up equals down, meaning the vectors are acting along the y direction, which in this case are going to be Fa sine theta, plus my normal force. Get rid of my mistakes again. Must be getting close to dinner time. That's going perpendicular to the surface upward, and that has to equal the component coming down, which is Fw cosine theta. Now, as far as along the x direction, which is parallel to the surface of the plane, I've got one force going up the plane, which is going to be Fa cosine of phi, and I've got two forces acting down, which is the force of friction, as well as Fw sine theta. And so we've got this equation, we've got this equation, and of course we always have mu equals F sub F over F sub N. And so at this point I begin to simplify my equations by plugging in whatever values the problem gives me. And we will stop there.